record on this computer. Alrighty. So, I don't know what this is. I'm just gonna share the entire screen. Okay. Okay, I saw two of you sitting outside, and they're still sitting outside. I can't believe these two. The Jay and the friend. Okay. Alrighty. So this is the Math 243 exam 3 review. Everybody is aware that we have an exam coming up, right? Math 243 exam 3 review for my Monday, Wednesday, Friday class. Your exam is on November 18th, which is a Monday. So today and Friday, we'll have reviews and quizzes only, okay? No new content. Now, let me bring your attention, if you have not been reading my announcements, which you should, okay? Math 243 ASU website. All the questions I pick are from here. Some of you have sent me questions to cover, which is great. Keep sending me more questions so I can cover it during Friday's review also. But some of them I've picked from the lecture notes or these 4 topics. You know the topics that are covered: function growth, modular, integer representation, Euclidean, and induction. Today's review will focus on, we'll touch base on function growth because I've already done this review with you guys. We had a paper quiz. Most of you, it seems, to understand this material, but I will do this review so that we are included this in the video. And today we'll focus on modular arithmetic, integer representation, Euclidean algorithm, okay? And the leftovers, if I have more questions, I'll cover it on Friday with induction. We have induction, yes. Induction and these 4, okay, are covered. Alrighty. So let's solve a few questions here. This is from the PDFs that are posted on, these are old notes. This is already done. You have this, yeah. I had a lot of extras for some reason. Okay, there you are. Alrighty. The number 1 question is modular exponentiation. I have to find the smallest positive integer n such that 3 to the power n mod 11 equals 1. So this is just a warm up, you know, an icebreaker before we head into the difficult modular exponentiation type problems. Can you find me the smallest n? Well, if I put n to be 1, 3 mod 11 is, you know the mod function? Yeah. Are you giving me the answer? Okay, I have to check that. How many agree with Nick? Oh, you got 5 too? Is it the smallest? Okay.
It's 3, 9, 27, 81, 243 is divisible by 11.
Perfect. There you go. So mod function, what happens with mod function? It gives you the remainder. It always gives you a positive integer at the end, right? And the answer, the remainder cannot be 11 itself. So it has to be 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 10. So when you divide 3 by 11, you'll get 3 back. When you divide 3 square with 11, you will get 3 square back because it's still less than 11. You can't divide. When you do 3 cube, like Nick said, 27 by 11, you will get 5 because 27 divided by 11 is remainder 5, but we want remainder 1. So I do 3, 4 mod 11. What was this, Nick? 81 mod 11 is 4. Yeah, remainder is 4, right? Because 77 goes into 11 and then remainder is 4. Make sense? Can everybody do this? Okay, but when I do 3 to the power 5 mod 11, I will get 1, right? The remainder is 1. Now, how does fast modular exponentiation helps me? Well, we'll see this. So for this question, if you get a multiple choice like this, you get n equals 5. Good? Using the previous result, modular arithmetic and laws of exponents, find 3 to the power 236 mod 11. Now for that, we have to look for patterns. See, they're not repeating yet, right? Nothing is repeating. Yes.
Just multiply the what's left by 3 and then divide that by 2. This is the only step.
Exactly. You already know 3 to the power 5, 3 to the power 5 mod 11 is equal to 1, right? We already know that. We figured it out. What is 236? Can I write 236 as some? This is what you do. Step 1. 236 can be written as 235 plus 1. Agree? And what is 235 as a multiple of 5? Divide this by 5, what do you get? 47. Why are we so focused on 5? This is the trick that we have to be very comfortable with. Okay? We are focused on 5 because 3 to the power 5 will become 1 eventually, right? So if I have 236, now step 1 done. So we move back to step 2. I'm looking for 3 to the power 236 mod 11. I'm going to break this up. I'm going to break this up as 235 plus 1 mod 11. And this process is crucial for any question you will get in exam. Is this clear to everyone? Any questions? Is this clear why we are doing this? Okay, why we focus on 5, not a multiple of 2? Okay, so now because it's plus, I can break it up. I can write it as 235 times 3 to the power 1. Okay, because it's a law of exponent, which is very common, but it's tough to make a connection, especially in exam. It's tough to make a connection. So remember this. At some point in these questions, you will be doing this. Okay, breaking up the powers. Good. Okay, then now I know this is 5 to the power. I can write this as 5 to the power 47 times 3 to the 1. Well, that's just 3, but I'm just writing it so that it's clear. Good. What is, and because the property of mod is, I can move it inside, I can break it up, and every sum or every multiplication gets the mod, individual mod, right? So this, I can rewrite this using the property of mod. I can do this, 3 to the power 5 mod 11 raised to that big power times 3 mod 11, right? And eventually what the answer will be, we will again apply mod 11. Because we are in this universe where we divide everything by 11 and record the remainder, right? What is 3 to the power 5 mod 11? You already know that's 1. What is 3 mod 11? That's just 3. 1 raised to whatever power doesn't matter. You just get 3 mod 11, which is 3. Okay. Now this question was broken up into subparts where it was given as a hint to you that 3 to the power 5 mod 11 eventually returns 1. And then we somehow broke up the question as multiples of 5 so that life is easy. Now these questions are not conceptually, you don't have to memorize a lot, but they require practice. Okay, they demand a lot of practice to get them flawless in the exam. Alrighty, clear so far? Let's do one more example. I have plenty of examples on fast modular exponentiation for today. Find 3 to the n mod 11 for the following values of n when n mod 5 is 0. N mod 5 0 is means or multiples of 5, right? N mod 5 0 means n is 0, yeah, 5, 10, 15, 20, 25, all of them, right? But it doesn't matter. This is what they are telling you, right? When n is all this, I know that my mod is 1, right? So for all of them, for 3 to the power n, whatever here, my answer will be. Let's do an example. Okay. Is this clear to everyone? And I will only ask you for questions where the modulus gives me 1. Otherwise, I won't. When I say n mod 5 is 0, this is nothing to do with the question above, okay? If I give you a general question and I say n mod 5 is 0, what does that tell you? That n divided by 5 leaves a remainder 0. So n could be 0. N has to be a multiple of 5 because when you divide by 5, remainder is 0. Make sense? Now I know 3 to the power 5 mod 11 is 1. Let's check. 3 to the power 0 mod 11 is again 1. Right? Because anything to the power 0 is. These are just trick questions, but if you just do at least one of them from the PDF, you will be aware if you see another one in the exam, okay? What if I do 3 to the power 10? Use the same trick that we used above. 3 to the power 10 is 3 to the power 5 squared. And 3 to the power 5 mod 11 is 1, right? Any multiple of 5, I can express it like this. Which rule I'm using? I'm using this rule. If I have a m to the power n, this becomes m times n, right? Now, this is one type of question. This is important for true, false, short answer type questions, multiple choice. Just be aware of the mod definition, okay? Now the long type, the free response type questions, what can you expect? Questions like this. Use fast modular exponentiation to calculate 201024 mod 13. And then how many squaring steps were performed in this algorithm? Question clear? Let's solve this. 2002 to the power 1024. We'll do it in, oh, I have more questions here. Okay, we'll find a blank page there. So I'm gonna do what was it? 1024 mod 13. That's what they want you to find, okay? The first thing you will do, if you see a question like this, is find the binary representation of 1024. Step 1. Step 1, write 1024 as powers of 2, as a sum of powers of 2. How do I do that? I don't have it in my notes. Somebody tell me. You keep dividing by 2, yeah, right? So that's something that we have to be very fast at. Watch my videos. I have videos on binary conversion on YouTube. It's very straightforward. It's a process that you have to practice. Oh, was it easier? Is it this? Okay, don't work hard, work smart in exam, okay? Sometimes I might just give you 1 power, right? 1024 is 2 to the power 10. So this was an easy question. I have some difficult ones also where it's supposed to be a sum, okay? Clear to everyone? When you will do the binomial, the binary representation, this is what you're supposed to do. You're supposed to keep dividing it by 2. So 5, 1, 2 plus 0, right? And then keep dividing it again and again. So this will be 256. Yeah. Plus 0. Then you keep doing this. Keep repeating it until this thing becomes 0. Okay, remainder could be anything. And then you go from, I have a video clearly explaining the entire lecture notes on this. Okay, so make sure you watch that. And then in this case, everything else is 0, is just the first one. So 2 to the power 10. Now that you have this, step 1 done. I have written the power as a power of 2 or sums of power of 2, which we will deal with. This is the first goal that you have to do. Okay? Because it's 2 to the power 10, you know what it means? It means that I need to square 2 10 times the first square 10 times to get this power. Okay? You know that there was a question, how many squaring steps we need? We need to square it 10 times. Good? The next thing you do is start looking for remainder patterns. That's step 2. Step 2, look for patterns. So what is 2, start with this pattern, 2 to the power, or, just leave it at this. I'm trying to find the easiest way to explain this. What is 2 mod 13? Just 2, right? How can I rewrite it? You don't have to do this in the exam, but I just want to make sure you understand how we are squaring it. How can I rewrite this? Or I could say 2 to the power 2 to the power 0 mod 13 equals 2, right? Eventually, you want to write down the pattern when the remainders start repeating. Is this clear? Can I write 2 to the power 1 as this? Can you make this connection? You sure? Can you make this an exam? Okay. Now, repeat it again. So what is 2 square mod 13? Well, that is 4, right? That's 2 to the power 1. Make sense? When I do the square again, you know what I'm doing? I'm going to do 4 square mod 13, which is nothing but 2 to the power 2 mod 13. What is 4 square? 16. 16 when divided by 13 gives remainder 3. Okay. Step 1, write the power as 2 to the power something or sums of that. Step 2, start looking for remainders. I just wanted to make this connection that 2 to the power 1 is nothing but 2 to the 0. Okay. Then every time you square, you are adding 1 to the power in each step. Okay. That's the connection I wanted to make. There are more examples in my lecture notes if you want to read. Now, the next one would be 3 square mod 13, right? The last entry gets squared each time. But what is that? This is nothing but 2 to the power cubed mod 13. What is 3 square? It's 9. It's not repeating. Okay, keep going. 9 square mod 13. In other words, that's 2 to the power 4. What is that? What is 81 mod 13? It's 3. Oh, perfect. Now we are repeating, right? We are repeating now. You see, I had a remainder 3 above. I got remainder 3 again. As soon as you hit a repeating remainder, you stop right there. Okay? Stop. Stop here because my remainders are repeating. Is this clear? You start with the original number, which is 2 to the power 0, and keep squaring it in each step. And you stop when you repeat a remainder. And after this, and this is also very important, you write down the pattern. This will help eliminate any mistakes you will do in your final step when you write down this pattern. Now, that's why I wanted to make this connection between 2 to the power 1 and this. See what happens when I try to write down the pattern that I just observed. If I have 2 raised to the power 2 to the power n, okay, and I'm doing mod 13, I am getting, how many possible answers I'm getting? I'm getting 2, 4, 3, 9, right? So I'm getting 2, 4, 3, 9. These are the possible remainders I will get. They keep on repeating after 3. Is this clear? When am I getting 2? I'm getting 2 when n was 0. You see why it's important to write it like this? When n was 0, I got remainder 2. When did I get remainder 4? When n was, where is it? When n was 1. That's a special case. 4 will never come back. When n was 1, I got remainder 4. When did I get remainder 3? When n is even. And when n is odd, I'm getting. No, you're right. It's even. Odd except 1. Right? Because 1 gives me 4. This pattern, I cannot emphasize how important this is to write this step, this little box right here. This is very important. If you have any questions, you ask me right now. I don't want you stuck or blanked out in exam. Good. We write down the pattern. We write down this function. Make sure you express every little thing there. And now you go back to the question, the final step. This is step 2. The final step, what do we really need? Which power did we need? Now this question was easy because it was just 1 power, mod 13, which was just 2 to the power 10, mod 13. And we already know the pattern. If the n is even, this should be, there you go. There you go. Good. I have more examples. I want to do more examples of this. This is an important concept. Now make sure we all are on the same page. Any questions? Let's do one more example. One more example, which, and I need your help. Okay, so keep your calculators out. Okay, let's do this one. I don't know, the 7. Let's try with 7. Question. I have 5, 130 mod 7. Very typical question. You can expect this in exam. Okay, something very similar. We'll solve it step by step together. I want you to copy the exact steps in exam. Okay. Alrighty. Step 1. First thing you want to do is write 130 as powers of 2. Now, if you remember some powers of 2 that is close enough, use those. 128 is a power of 2, right? What is that power? Good job. Are you sure? How many agree with Daniel? Okay. Is 2 to the power 7 plus 2 to the power, yeah, 2 or to the power 1, right? We want to continue with writing 2 to the power 1. Good. If you cannot think of this, then unfortunately, you'll have to do the binary thing, which I know everybody hates. I hate that too. I cannot blame you, but this is our only choice. So, you know, what is this? 32 plus 1. 32 is 2 to the 16. This is just a quick refresher of how to do by a binary representation, right? 2, 8 plus 0. 8 is 2, 4 plus 0. 4 is 2, 2 plus 0. 2 is 2 times 1 plus 0. 1 is, now I have to stop. I can only stop when I have the quotient 0. Okay, make sure you do enough practice for this. So the binomial representation, if you cannot think of this, if you can think of this mentally, be my guest. I don't require you to show your work. Okay, if you can find this on your own, perfect, do that. Sometimes it's difficult, so do this. All right, I will not give you a big number in exam, so you should be able to do it mentally. Okay, now step 1 done. Step 2 is now I start looking for patterns. So I start with 5 mod 7, which is nothing but, because 5 divided by 7 leaves a remainder of 5. You cannot divide 5 by 7. Okay, it gets 5 back. Now here's a little thing that I want you to remember. 5 is nothing but 5 2 to the power 0. Just have that little connection in your mind that 5 to the power 1 is nothing but 5 raised to the power 2 to the 0. Okay. Alrighty. Now I square it. So I square it, I get 5 squared mod 7 is what? This 5 moves here. Is it 4? 4 it is. Right? And just, just keeping this little thing on the side, 5 square is what? Is 5 2 to the power 1. Good? Just have this connection going on. You will need it later on. Now, next we move this thing and square it. What is 4 square mod 7? No.
No, it would be 2.
Okay, make sure you double check your math, okay? It's 2. I am relying on you, so you better give me correct answers.
6.
Exactly. You know what is this? What is happening here? This is 5 2 to the power 2. Each step you are getting this power, okay? This means 5 2 to the power 2 mod 7 is 2. Make sense? Make this connection in exam. Now again, we're going to repeat it. Question?
5 to the power.
This is exactly great question. 5 to the power 3 is this. We are squaring it, right? We are squaring 5 square again. We are not doing 5 to the power 3. We are doing fast exponentiation. So that's the important part. You're not going like this. You're not doing 5, then 5 square, then 5 3. That's slow.
Yeah, but it's different. 5 to the power of 3 mod 7 is 6.
No, this is not what we're doing. Okay, we are doing this. We are doing 5 squared, 5 squared squared, then 5 squared squared squared. We are doing fast squaring. Otherwise, if you were doing the regular square, that's a great question. That's in my video also, okay? If you were doing the regular squares, you know how long it would take to get 1024? You would have to do 2 times 2 times 2 times 2 again and again, 1023 times. That's called slow exponentiation. We are not doing this. You see the difference here? We are squaring each step. Hence, the powers of 2 are increasing. At first, we have 2 to the power 0. I square the whole thing. I get 2 to the power 1. Square the whole thing. I get 2 to the power 2. Square the whole thing. That was a great question. But do you see the difference? That's why each step, I'm squaring it again. Okay? There's a difference. We're not multiplying. We are squaring each step. So each step gets squared again. Clear? It's a very crucial difference, very subtle. Okay, so I'm squaring 2 again, which gives me one more power, which is 2 square mod 7 is? No. J? 4. What is happening with you? Okay, so this is 5 2 to the power 3. You see how it's increasing? The powers of 2 in the exponent are increasing because you're doing a fast squaring at each step. It maps to each of those. Exactly. Exactly. Instead of doing this, I'm doing the last remainder because it's mod function, right? I can replace it with the previous remainder. Just do exactly the same. Good. My remainders have started repeating. So that is the hint to stop. Okay, is this clear to everyone? Can you do this? Write your power as powers of 2. Keep squaring. Keep squaring. No, you're not multiplying by 5. You're squaring each remainder. Got it? And can you make the mapping in your mind? Alrighty. So now the next thing is I write down the the patterns that we observed. Okay, so write down the patterns. If I have 5, 2 to the power n mod 7, you know what will happen? I'm getting, what do I get? 5, 4. I only got 5 to 4, right? Okay, so 5 when is 0. 2 is when? Look at this side. Look at this even, right? When n is even, and 4 when it's odd. So that's why I want you to make this mapping on the side to make sure you collect the right numbers. Okay, good. At the back. Alrighty. So what did we want in the question? Now here comes this is a trick question, right? This was more difficult than the last one. The final answer is what the question actually wanted. The final answer was 5,130. That's what we are interested in. All this math to find this value. But we know that this is 2 to the power 7 plus 2 to the power 1. And that's how we break it up. Good. So 5 to the power 7 is nothing but, I can write it like this, mod 7, right? And because it's the mod function, I can distribute it. So this is equal to 5 to the power 7 mod 7, 5 to the power 1 mod 7. And I already know the pattern. If n is odd, this answer will be 4. If n is, well, that's again odd, right? Mod 7, and 16 mod 7 is 2. So these questions are going to be long, expensive, but they follow a simple procedure. All you have to do is memorize the 3 steps, okay? And make sure your math is correct. Don't do 16 mod 7 is 4. Yes. Great question. Yes, because that's what fits our pattern. That's what fits every pattern. If you keep squaring a number, square, square, right? Square, square again. This fits our pattern. We start with 0, 1, then it keeps increasing. I'm pretty sure you can do 3 to the power also. You can do this, but there are many ways to solve these problems. This is the fastest. Okay. Alrighty. So this is one example that I had for you guys. If you want to practice more, you can do this one at home. Question. Because 16 divided by 7, what's the remainder? Don't do 4, okay? That's a very common, I cannot tell you how many times I see 4, like Jay does, right? Okay, try this, there are plenty of questions. If you go to Google and say fast modular exponentiation example, you'll get plenty of questions. The video will be there. Watch the video, solve more questions, okay? Do step 1, step 2, write down the function. The green box is very, very, very important. Write down this part, question, yes. Yeah, I'm covering. I'm getting there. I'm getting there. This is the most important question that I want you to study. Okay, try this yourself, or maybe I'll give you a quiz later. Now, the mod properties that he was, I thought I wrote. Okay, let's do a brush up on modular properties, mod and diff function, because we don't want to leave the diff behind. Right? What is diff function? Exactly. Okay, here's a little question for you. What is 16 mod 3? Said Akash, focus here. Study after. Yeah, it's 1. Right? Modular function will always give remainder positive and an integer. What is Negative 24 div 5. What is div function? It's the ceiling or floor? Floor, right? You go smaller. Negative 24 divided by 5, floor of it. Remember this, okay? Diff function is floor. What do you get? No, that's different. That's a different concept. What is negative 24 divided by 5? Do use the calculator. Negative 5. No, that's a different concept. That's pigeonhole principle. You're combining two concepts here. Is it negative 4 point something? And what is the floor of that? Just leave it at negative 5, okay? No plus 1 here. No plus 1. What happened? Right? Alex, all good? That's what you said? Oh, never mind. Okay, sorry, my bad. Okay? Okay, let's do one more. 14 div 3. You know what you're doing, really? You're doing this. This is the mod, this is the diff function. Okay? But this is faster to remember. Whenever I use diff function, you know what to do. Find the floor, and negatives are the most difficult ones because negatives you have to be careful. You're going one down, right? What if I combine this? What if I said 16 mod 3, okay, plus negative 24 div 5. And the whole of it is mod 3 again. Then what? 16 mod 3, you found out above, is 1. 24, negative 24 div 5, you found out is, what am I doing with the whole thing? Think again before you answer. The final is mod. Cannot have negatives in mod. No negatives. Exactly, right? You know what you're doing? You're looking for a quotient here such that the remainder is positive. What are you doing? Negative 2 plus 2. So this is, if you write a negative here in mod function, I'll be mad. Mod function, always positive. Div, we could not care less. Okay? Make sense? If you see a question, practice more. There are more, or find more examples online or in the textbook slides that are posted under Canvas. Practice more. But it all comes down to finding mod and diff function. Be proficient with that. Alrighty. This is all the properties that you need to know. Next, what I have more questions that somebody asked, which is important. I thought I should cover here, these ones. What is the smallest positive integer m such that this number right here on your screen, this is taken from the Math 243 PDF. What is a perfect square? Come on. That you can take a square root of, right? So each power should be a multiple of 2. So what should be m to make it a perfect square? The smallest one. See, 3 to the power 4 is already a multiple of 2. 7 to the 3 is not a multiple of 2. So to make it a perfect square, I need to multiply by 7. And I need to multiply by 11 to make it a perfect square. So m should be 7 times 11, 77. Make sense? Perfect square means every power is a multiple of 2. or every prime factor? Good? Abdul. You're not taking the highest exponent. You're taking all exponents that are not squared. So it's not even, right? So I need to multiply by one more. Only one more, not more than that. Same thing here. What if I wanted a cubic number? What if I want a perfect cube? Multiple of 3, right? So this is not going to work. 7 cube is fine. 11, 7 is not fine. So what do I need to multiply it with? 3 squared also, right? And 11 squared. Because if I do 3 squared, this will become 6. If I do 11 squared, this will become 9. So m has to be 3 squared times 11 squared. Make sense? And you pick the correct answer based on that. Perfect square, every power should be a multiple of 2. Perfect cube, every power should be a multiple of 3. What is a GCD here? Now I've done plenty of examples with you guys, finding GCD, LCM, and all those stuff. GCD, you take the minimum power, in this case is 5 to the 1, and 7 to the, there is no 3, so 3 to the power is 0. Okay, LCM, on the other hand, is where you take the maximum power. So 3 to the 1, 7 to the 9, 5 to the 2. Pick max powers, pick min powers. Okay? Remember this? Solve examples from the lecture notes. I thought I had one more. Okay, Euclidean algorithm to evaluate the GCD. I have an example in my lecture notes. I have an example here, which I recommend you solve. I think I was going to add this as a exercise. So you know what you're doing. Take the bigger one, divide it by the smaller one, note down the remainder. Okay, then you move it here, then divide it by this, and you keep doing it until, wait, is it done already? Oh, my bad. So the GCD is the quotient, or this, I don't remember, but read my lecture notes, okay? 3 is the GCD of 1002 and 999. Good. I want to go back to the function growth quickly because I want to cover that. I don't want to post too many videos on YouTube. Okay, we remember this graph. I went over this before our paper quiz, right? I went over this graph before our paper quiz. Yeah. Well, you remember this graph now, okay? Higher the function, slower the algorithm will be, okay? Slower the code. Alrighty. Even if I do log x to the power 1000, will it grow faster or slower than x? Even if I do power 1000, this is same as 1000 log x, which is still going to be slower than x, okay? Log x raised to whatever power, if it's a number, is going to be less than x, okay? Below the graph. This is where it gets a lot confusing, where you have to do this. You have suppose I give you this, x cube yeah, I know that. I mean, you get the point, right? It's just everybody understands this differently. Okay, I have x cube and x log x, okay? I'm saying x cube log x is blank x cube. What is a fill in the blank? X cube is blank. How do you connect big O and big omega if I flip the functions around? The definitions change. For this, I had the other three graphs. Keep this question in mind, okay? I will come back to it. Now look at here. You have to remember these two graphs. Big O means Fn is gonna grow slower than Gn, right? So when I'm saying this, x cube is big O where? At the bottom or top? How many agree with Daniel? Big O means if this is F, this is G, F is big O of G.
First function, because you're multiplying with the logarithm, it's gonna be a worse algorithm, so that's basically. This x cubed and then big O at the bottom.
Make sense? This is where it gets most confusing. So make sure you at least remember, as soon as you get the exam, write this on your top of the paper, okay? If I reverse it, it becomes, you see the difference? We are using these, I will post all these notes on Canvas, but this is what I want you to, these graphs, I'll post them, but they matter. If you reverse the function, the big O, big omega definitions change. Okay, now I wish there was something to memorize this, but unfortunately there isn't. If I give you a polynomial, what will you do? Waste your time or what? Take the biggest power? Exactly. If I give you a polynomial without wasting your time, it's theta x squared, it's big O x squared, it's big omega x squared. Okay? Nobody will spend a minute if you see a question like this.
Big O and the big match.
It's theta. Yes, yes. If I gave you this, if I gave you log 17 to the power x cube, it's x cube, right? It's x cube times log 17. So be careful. There will be easy questions. They're very easy. You should not waste a minute on these questions. But they'll just, they'll be, what do you call it, camouflage. Yes, my bad. It's just power of this. Okay? You got it. You got what I'm trying to say. Right? Okay, this is one question that I want you to solve. Before we leave, I know we have to go back home. Let's solve this one. Come on, somebody gives me the answer. What is big O here? What is big O? Look, there are two functions here, xx, 2x plus xx, x squared. What is the dominating function? This guy right here. Right? Big O of this guy. What about this one? X factorial is the fastest growing. What about this one? Quickly, should not take you more than 2 minutes. X factorial x. Okay, what if I ask you to write this in increasing order? Which one is the slowest? Quick, quick, quick. H of x is the slowest, which is higher than h of x. Which is higher than g of x. Right? Because x factorial grows fastest. X factorial times x to the power 4. Right? No, h of x is not the, is g of x. Is g, correct. Daniel, you give me the wrong answer. Okay, good. Make sense to everyone? Okay, we'll continue with more questions of induction in next review.